is the fourth lecture on quantum Schrodinger equation. We were discussing about the boundary condition to be satisfied by the wave function and few applications. In the last class, we have applied, we have solved the Schrodinger equation for 1D free particle, and there were no boundaries, so there was no question of applying boundary condition, and we found the solution is of this form, I to the power ik plus minus ikx. So we put a superscript plus minus to indicate the which sign we are considering, and it is found that this solution are the eigenfunctions of p having eigenvalues plus minus p. That is to say, plus sign corresponds to a free particle moving towards the right, and minus sign corresponds to a particle moving towards the left, and there is no quantization. That is to say, the energy spectrum is continuous, no quantization. Secondly, we applied the Schrodinger equation and solved time independent Schrodinger equation for a particle within a 1D box. This may be may be said to be a 1D box or a 1D infinite well, whatever. The solution was this, with energy value this, and this is the quantization units of energy. We found that the energy value was energy values are quantized. You note that we applied boundary condition only on the wave function but not on its derivative, because at the walls impulsive force acts on the particles, so momentum is not continuous, so we did not apply any continuity condition of the momentum at the point of discontinuity. As the third example of this kind, we use 1D step potential, where we will apply boundary condition on the wave function as well as its first derivative and see what we get. So let me describe the system first. 1D step potential. So this is our topic today, and we shall find something very new in this example. 1D step potential. The situation is there is a constant potential V1, and at a point there is a jump in potential, the potential goes to V2. So if we draw the potential axis, it is the this is V1, it is the point A, and this is for V2 potential, it is the V axis, and this is X axis. Without any loss of generality and to simplify mathematics, we can transform this situation into such a situation. This is x is equal to 0. This is X axis. Here the potential is 0, and here the potential is V. Actually, so then V is equal to V2 minus V1. These two situations are identical. Only thing that the mathematics involved would involve A and will come to be a bit complicated compared to this, but these are two physically identical situations. So to simplify mathematics, we shall stick to this description. So this is the step potential problem. This is potential is V. So there are two regions. One region is towards the left of the origin. This is called region 1, and this is region 2. In region 1, the potential is 0. potential is 0, so it is a free particle. We initialize the system to be like this. A free particle is moving towards the right and approaches the step located at the origin. So initialization is a free particle moving along positive x direction encounters the step potential at x is equal to 0. So initially the system is that a free particle is moving along this direction. Now there is a discontinuity at x is equal to 0. Since the discontinuity is of finite amount, the wave function as well as its derivative will be continuous. Phi 1 at 0 is equal to phi 2 at 0. What is phi 1? The wave function in this region is written as phi 1 because this is region 1, and the wave function in this region is written as phi 2. So this is the wave function in region 1 and this is the wave function in region 2. They should match at the boundary, and second boundary condition is phi 1 prime at x is equal to 0 is equal to phi 2 prime at x is equal to 0. So f phi 2 prime at x is equal to 0. So this is the continuity condition of the first derivative. Now let me write the Schrodinger equation, time independent Schrodinger equation for region 1. Region 1 extends from x less than equal to 0 towards the left, and in this region potential is 0, and the wave function is, as I have stated, it is phi 1. So the Schrodinger equation is minus h line square by 2m d2 phi 1 dx2 is equal to e phi 1, or this is phi 1 double prime plus k1 square phi 1 is equal to 0, where k1 square is equal to twice m e upon h line square and is a positive quantity. So the solution is phi 1 of x. Now again we can write the solution in two ways. One is in the form of traveling wave, and another one is in the form of stationary waves. This is K prime x. Which one should I opt? Here the system is like that. A free particle is moving and approaching the step. So a free particle is represented by a plane wave. So this is a good representation of the incident wave. And on encountering the step, a part is reflected out. So this is incident and a part is reflected out back. So this may be treated as a reflected wave. In that sense, we are not opting this solution, but we are opting this solution and identify that this is the phi incident and this is the reflected wave. Coming to the region 2, The solution of region 2 will depend on the relative value of V and E. If E is greater than V0, if this is greater than V0, if this is E which is greater than V, this is V0, so if it is greater than V0, then the solution will be sinusoidal in region 2, and we consider this case first. So let me summarize, keep this in. Let us note the summary of this. Phi 1 x is equal to a e to the power I k1 x plus b e to the power minus I k1 x. The region of validity was x less than equal to 0. This is incident wave. This is incident wave. This is reflected wave, and k1 x less than equal to 0 with k1 square is equal to twice me upon h line square. Now for region 2, we first assume that E is greater than V0. So this is case 1. So what will be the Schrodinger equation in region 2? The Schrodinger equation in region 2 will be, this is time independent Schrodinger equation, plus V0 phi 2 is equal to E phi 2, and the region of applicability is x greater than 0. The solution can be written as in this form: phi 2 or we write it as where k2 square is twice m e minus v0 by h line square. As per our assumption, E is greater than V0, so this is essentially a positive quantity. The solution is phi 2 of x is equal to c e to the power plus I k2x plus d e to the power minus I k2x, and region of applicability is this. You know what is this wave? This is the incident wave in region 1, this is the reflected wave in region 2, this is a transmitted wave in region 3, this is the transmitted wave in region 3. So this should be identified with transmitted wave, but it represents a wave traveling along the negative x direction in region 2. Once the particle comes to region 2, there is no more discontinuity in the potential, so there is no question of getting reflected wave or wave traveling in the negative x direction in region 2. So this is unphysical, and we set d is equal to 0. Such wave could arise only if the situation is like this. Then a certain wave is coming, and in this region, this is the wave traveling towards the right, which is this, and a part will be reflected, and this is represented by this. But there is no such second discontinuity to the right of the origin. So this is unphysical, and we conclude the solution to be this. So we got the solution. One solution is this, and this is the other solution, and this is the transmitted wave. Note that we could also identify the situation, what is going on. This is incident wave, reflected wave, transmitted wave. Now let me apply the boundary condition. Before going to this, I am writing the summary once again. The summary is that for E greater than V0, phi 2 of x is equal to c e to the power plus I k2 x, where k2 square twice m e minus v0 upon h line square. The first boundary condition. Phi 1 at 0 gives you phi 2 at 0. So continuity. So from this we get A plus B is equal to C. A plus B is equal to C. Now phi 1 prime at 0 is equal to phi 2 prime at 0. If we differentiate it with respect to x, I will get this term will be plus ik1 times this, and this will be minus ik1 times this. And when we put x is equal to 0, the condition becomes I k1 a minus b is equal to I k2 c. We draw this two, or a minus b is equal to k2 by k1 c. If we call this equation 1 and this is equation 2, if we add, we get 2a is equal to k1 plus k2 by k1c, sorry, c, or c by a is equal to 2k1 by k1 plus k2. And if we put this condition, if we put the value of c in this equation, we get b by a is equal to k1 minus k2 by k1 plus k2. These are the solutions. Now you know that there are basically three unknowns. If the potential well is specified, then V0 is known, and for a particle of given energy E is known. In that sense, K1, K2 is known, since the particle mass of the particle is also known. So K1, K2 is known. So in this equation, 1 and 2 involves three unknowns, A, B, C. But we have only two boundary conditions, and which cannot give you A, B, C in terms of K1, K2. But we can determine B and C in terms of A. What does A signify? Let me first come to this point. Now this is a plane wave, so the probability current density that is what we are trying. This is corresponding to the incident wave. This is given by K1 A modulus square H cross K1 times M, and this is positive x direction. So this is the particle flux or intensity of the incoming particle. So what is the number of particles that is coming to the well from the left per unit time? It is its measure. Similarly, the probability current density for the reflected wave is H line K1 B modulus square by M, but in this time it is along minus x direction. And finally, probability current density for the transmitted wave you note that in the we calculated the probability current density for the plane wave associated with the plane wave to be like this, H cross K vector A modulus square by M, and K vector is the propagation vector for the incident wave. It is along positive x direction, so we have indicated the unit vector as x cap, so it is along positive x direction, this is along negative x direction, this is again along positive x direction. So the question is that what is the fraction of the incident wave that is being reflected? So if one throws one crores of identical particles in this direction, one after another, how many of them will be reflected in region 2? This is called the reflection coefficient. This is governed by the reflection coefficient. Similarly, the transmission coefficient, that is what is the fraction of the incident wave that is being transmitted to region 1. In this case, remember that it is a probabilistic theory. So, if you consider that a single particle is being thrown in this direction, then if the particle is getting reflected, how can it be transmitted, the same particle? No, the theory says that if you allow a large number of particles to identical particle to come along positive x direction and to face the step at O, then on the statistic, on large scale, how many of them will be reflected and how many of them will be transmitted. So this is a statistical theory. That means this prediction of the theory will hold good only when the number of events is extremely large. And from this relation, that K1 same, because in this region 1 the wave vector is K1, so this is simply B by A modulus square. Similarly, if we go to transmittance, this is reflectance and this is transmittance. We find that we use this relation. So the conclusion is that although we cannot find out ABC in terms of C1, C2, but in terms of K1, K2, but we can calculate the physically measurable quantity reflectance and transmittance out of these two boundary conditions, which allows us to find out the relative magnitude of C with respect to A and that of B with respect to A, and which enables us to get the result. The reflectance is okay. Now the reflectance is B by A modulus square. So this is simply K2 minus K1 by K2. Sorry, this is K1 minus K2. And transmittance is C. For C by A it is 2 k1 by k1 plus k2 whole square. So this is 4k1 square, which we can write it as 4k1 k2 by k1 plus k2 whole square. One interesting thing is that r plus t is equal to, from r we get in the numerator k1 minus k2 whole square, and from t we get 4k1 k2, and the denominator is same for both k1 plus k2 whole square. So this is 1. So the total probability is 1. So if you throw a large number of particles towards the well, either the particle is reflected or it is transmitted, because there is no provision for the particle to be getting absorbed. Another thing is that this quantity, note that the definition of k, the k1, if we consider k1 and k2 to be positive, then the magnitude of k1 is greater than that of k2. In that sense, this is greater than 1. It may appear to be astonishing that the amplitude of the transmitted wave is greater than that of the incident wave. Here we should think of in terms of probability current density. It is found that the probability current density of the transmitted wave is less than that of the incident wave. So this is one way of explaining the things. And if we draw the waves in this region, this is incident wave, this is reflected wave, this is incident wave, this is reflected wave, this is the transmitted wave. And another thing, the wavelength lambda is inversely proportional to k's. So since this k is if we consider lambda 1 is greater than lambda 2, where lambda 1 is the de Broglie wavelength in this region, this is lambda 1. Same for this, and this is this is lambda 2. Since k1 is greater, since k1 is greater than k2, that leads to lambda 1 less than lambda 2, and that is being written over here. This is lambda 2 is larger than lambda 1, so de Broglie wave is have larger wavelength in region 2. In this case, if one makes observation in asymptotic region here, that is at plus infinity, he finds the particle, and the particle flux in this region is given by this. And if one observes the particle in the negative extends to negative infinity, minus infinity, this is the probability of finding the wave. So here the probability current density is a very important thing. Now look at the situation from classical point of view. From classically, a particle is coming and encountering the barrier with energy E greater than the barrier height. So according to classical mechanics, every particle should overcome the barrier and come to the region 2. But here it is found that not all the particles, although it is accessible classically, not all the particle comes to region 2. Some of them are reflected from the boundary. This is because of the wave nature. The particles are being represented by wave. And if we draw this curve, it will be interesting to note the variation. This is 1, this is 0. Initially, it is found that the reflection is the important process, and as energy of the particle increases, the transmission becomes the possible process at each time. This is r plus t is equal to 1. This is x. Initially, if we consider the particle with low energy, then the reflection will be a dominant process. As the energy increases, the reflection will go on losing its importance, and transmission will be prominent. This case, when E is greater than 0, this is called scattering case, because the particle is obtained even at infinity. So this is called scattering case. It is the scattering case. Now let me come to the other situation when E is less than V0. Now if we consider the second situation, E less than V0, the solution of Schrodinger equation in region 1 will remain unchanged. Only thing, the solution in region 2 will undergo a change. And let me see what happens. Here we consider the particle energy is less than V0. So this is the total energy of the particle, and this is, we consider E less than V0. This is the V0 line. Now if we consider case 2, E less than V0 for region 2. Now note that in this region kinetic energy T, K, E is negative. So the particle, this region is classically forbidden, classical region. That is to say, if the particle with energy less than the barrier height impinges on a barrier, classically it is not possible for the particle to come to region 2, because in region 2 it will have negative kinetic energy, which leads to an imaginary velocity, which is not possible. So in this case, region 2 is classically forbidden. As kinetic energy is negative. Now we see what quantum mechanics predicts in this situation, and can it be corroborated through experimental findings. Let me first write the Schrodinger equation in region 2. The Schrodinger equation in region 2 is again h line square by twice m phi 2 double prime plus V0 phi 2 E of phi 2. Note that this phi 2 is not the phi 2 that we were talking for the scattering case. However, if we rewrite it, here we have written V0 first and E, and I put a negative sign. So since V0 is greater than E, it is a positive quantity, or we write it as phi 2 double prime minus rho square phi 2 is equal to 0, where rho square is twice m V0 minus E by h line square, and it is a positive quantity. Since V0 is greater than 0, this is a positive quantity, and the solution of it, as we know from our knowledge on differential equation, is of this sort: C e to the power I rho x plus d e to the power minus rho x. Note again, this c has nothing to do with the c that we considered in the earlier case. This represents a wave which decays exponentially in region 2. That is, in this region this wave decays like this, and this wave increases like this, which is unphysical. So this is, as this is not possible, we are entering into the classically forbidden region, and still the probability of getting the particle is increases as we go deeper and deeper into the forbidden region, which is not possible. So we discard this, and the equation is this. So the phi 2 in this case, for E less than V0, phi 2 at x is equal to c e to the power minus rho x, with the region of applicability this, and rho square h line square. Now let me first again apply the boundary condition. The first boundary condition is the continuity of the wave function at x is equal to 0. The continuity of the wave function phi 1 at 0 is equal to phi 2 at 0 gives you a plus b is equal to c, a plus b is equal to c, and phi 1 prime and 0 is equal to phi 2 prime and 0 gives you, from this side I get I k1 a minus b is equal to, if we differentiate this, it will be minus c, minus rho c, or I can write it a minus b is equal to minus rho c by I k1. This is equal to, if we take I on the numerator, this is I rho by k1c. You note that this expression is exactly similar to the earlier one if we replace k2 by I rho. So we can get the corresponding quantity. So if we add these two, I get an expression for C if we add 1 plus 2, we get 2a is equal to 1 plus I rho k1c is equal to k1 Since k1 is not 0, if k1 has to be 0, then the particle energy has to be 0, which is not possible. K1 is not 0. As we are impinging particle to the step potential, and which is denoted by, which is characterized by A, so A is not 0, so the right hand side is not equal to 0. So what is the probability of finding the particle in region 2? Probability of finding the particle in region 2. This is given by P2. I am not using this concept, rho, as it may create confusion with it. So this is it shows that the probability of getting the particle in classically forbidden region is not zero, but it decreases decreases rapidly with increasing distance into the region 2. That is to say, if we call the probability plot phi 2 star phi 2, it decays in this fashion. This is 0, this is x. Similar thing is observed in the case of metallic reflection. When an electromagnetic wave enters into a metal surface, it is found that the electric field and the magnetic field becomes zero on penetrating a certain distance into the metal. The larger the conductivity, the smaller is the depth up to which the wave can penetrate. This is called skin depth, and the effect is called skin effect. Skin depth and skin effect. The situation in metallic reflection is visualized due to like this. In a metal there are successive layers on which the atoms are placed. Because of the lustrity of the metal, when an electromagnetic wave falls on it, a greater portion or a larger section part of the incident wave is reflected back. A small fraction is refracted into the second layer, and it gets reflected from this. If we consider such few successive reflection, the entire energy of the incident light is being reflected back. So in metallic reflection, the skin effect is visualized as the successive reflection from the crystal planes. Here there is no such crystal plane. Still, we can think of the situation as this. The particle enters into the classical forbidden region. There are some imaginary line, imaginary boundary which reflects most of the particle that is entering in this forbidden region back into the first region. The small fraction which survives is getting reflected by the second imaginary line, and so on and so forth. And we measure and how far the wave is penetrating into the second medium can be measured by a quantity delta is equal to 1 by rho. So if we put x is equal to delta, then the wave in the second region reduces to 1 upon e times of its surface value, and it could be considered as a measure of the penetration. The larger the value of delta, the larger will be the penetration into the forbidden region. If one wants to calculate the probability current density corresponding to this wave, he will get a zero value. As the wave is getting decayed exponentially, one will get nothing in asymptotic region. This is the theory. What is the main point is that the quantum particle can penetrate into the region which is classically forbidden. This is the prediction of quantum mechanics. Can it be corroborated or can it be verified by experiment? Yes, it explains one of the unsolved problems of physics, that is the nuclear disintegration or the alpha radiation like this. If we consider the alpha particle, where the alpha particles within the nucleus, they are bound by strong nucleon forces, and we may assume that alpha particle to be within a spherical well, so that the potential exists from r is equal to 0 to r, small r is equal to 0 to r, right up to r. This is the region within which, this is the spherical region within which the alpha particles are confined. If we and at this bound, in this region, the potential is negative potential is constant, and in the outside of this the potential is another constant. If we translate this three-dimensional picture into a one-dimensional picture, the situation looks like this. This is the this is the width of the well, and the particle is confined within a well of finite width. If we, for the time being, we forgets the left head, then this situation is similar to the step potential. So consider a free particle here, and it is it possible to for the particle to come to the second region when the total energy of the particle is less than the barrier height? In alpha disintegration, it is found that the particles of the alpha part, the energy of the alpha particle is less than the barrier height. So classically, there should be no alpha particle on the outside the nucleus. But experimentally, we get the alpha particle, which stands in favor of the theory that we have just predicted. So how could one visualize the situation? One visualize the situation like this. This is the potential height V0. If we think classically, the particle, if the particle wants to come to region 2 from the it has to cross this height V0. But one thing can be done. A tunnel is digged between this, and the particles comes to region 2, even if it doesn't have a sufficient energy to surmount the barrier. Such a phenomena is called tunneling. So the theory that we have just worked out is the quantum tunneling. Tunneling, which explains alpha decay. So let me conclude the situation. If we solve the one-dimensional step potential problem, where we can apply the continuity condition of the wave function as well as the first derivative, we see that there is no quantization effect. Only thing is that if the energy E is greater than V0, the scattering case occurs. So some of the incident wave is reflected and some of the incident wave is transmitted in the region 2, so that the total probability is conserved. And if the total energy be less than V0, then on the whole the entire wave incident is getting reflected, but the reflection does not take place right from the boundary. Some particle penetrates into classical forbidden region and gets reflected in successive steps, so that ultimately all the particles are being pushed back into the region 2. Still some may come to this, and if one may perform some observation very close to the origin on the right, there is a finite probability of getting the particle on this there, and which explains the alpha decay problem, and the phenomena is refers to as the quantum tunneling.